So in this three-phase grid connection system, we would like to replace all these controller blocks, and we would like to have all the variables in the controller region as DC. How do we do that? Because all the signals that you are sensing are AC signals. How to go about doing this transformation? So let me remove this and let me draw a line. Above the line, all the variables are AC. Below the line, I want to convert all the signals through some transformation where it becomes DC here. So that is the AC domain, and this region will be the DC domain. So I will put a transformator and convert all these signals. Let us say the currents that you are sensing are sinusoidal signals, and after you pass it through this transformation, what we call frame transformation, the variable here, even the current variable here, will appear DC. So to the controller, as the variables are appearing DC, I can now make a set point controller. Now that would give a much better response, and the controller will also be simpler and have a better bandwidth and better performance. To do that, we will discuss this DQ axis theory. There is this DQ axis theory whereby it is a transformation principle where you can convert AC signals into DC, AC sinusoidal signals into DC, and then operate upon the DC values, and then back again transform it into the AC domain where they will become AC signals. So this process of transforming from AC domain to DC domain, DC domain to AC domain is what is popularly known as DQ axis theory, which we will see now. Consider an axis here like this. I will not name it now, I will name it later. Just consider an axis here, and consider a time axis here as shown, and another time axis also I am drawing here by the side of it. Now let me draw a sine wave like this on this time axis. Likewise, I will repeat that sine wave on this time axis too. Now here, not only am I drawing a sine wave, I will also have a cosine wave, cos wave. So let me mark and draw a cos wave like this. As this sine wave is evolving with time, at every instant of time it is having a value, and project that value onto this axis that we drew first. So if you see that there will be a projected image on this axis as time evolves, and that will be in this region depending upon the amplitude of this sine wave. Now I will draw another orthogonal axis like this. I will still not give this also a name, I will give that later, but it is an orthogonal axis. So this sine was placed on a plane which is vertical. I will have a horizontal plane like this, and on that horizontal plane I will place this cos wave like this. So you will have to imagine the cos wave is placed on the horizontal plane, the sine wave is placed on the vertical plane. So they are placed onto orthogonal planes. Just like you did for the sine wave, as the time is evolving, the cos wave, the projection of the cos wave is seen on this axis, this orthogonal axis, as we are as I have shown here. So in a cycle, as the cos wave has evolved like this, you will see the projection as a line on this axis like this. Consider the cos and sine signals here. Now assume that this line, vertical line, gray shaded line, is moving with time along like this. I'm going to move this gray shaded line at different points in time. I'm going to sweep it in the time axis. So let us say at this point in time, let us say this is 0. Let us see what is the projection. When it is here at this point, the sine wave value is 0, the cos wave value is maximum. So if you look at it, the sine wave value is 0, its projection is on this axis, it will be here. The cos wave magnitude is maximum, and on this plane it's maximum, its projection is here. And I will put a mark here to represent the vectorial sum of this point on this coordinate axis and also this point on this coordinate axis. Now I will shift this reference line right like this. Now at this point in time, the sine and the cos values are like this at the point of intersection. Now if you take the sine, which is on the vertical plane, the corresponding point is here, and on the horizontal plane the corresponding point for the y is here. Both is at the same time. Now project the cos point onto this axis, project the sine point onto the vertical axis, and you will see that those two combine and the resultant will be a vector like this. So this would be a cos value, this is a sine value, and therefore this would be root of cos square plus sine square of the angle, which is 1 if both the sine and cos are unit sines and unit coses. Now I have moved this reference line further, and I see that here the cos time signal is at 0 at this point, and the sine time signal is at maximum. Now coming back to this orthogonal plane representation, you will see that the cos signal has reached 0 in the horizontal plane, the sine signal has reached maximum on the vertical plane, and now you project the sine signal onto this axis, project the cos signal onto this axis, then you will see that because the cos signal value is 0, the resultant marker will be there and the vector will be at this point. Here again cos signal is having 0, sine signal is having a maximum value. If they are unit sine and unit cosine, then the max value will be 1. So you see that the vectors are all amplitude 1, amplitude 1, amplitude 1, so on. And if we proceed, you will see that it will start moving along this locus. The tip of the vector will move on this locus, and the radius of this circle will be 1. It will in fact be a circle, because every other intermediate point can be reached by root of cos square theta plus sine square theta, which will be 1. So this coordinate axis which I have here, this coordinate axis is a spatial coordinate system. I will now call this axis by a symbol named alpha axis, and this vertical axis I will call it as the beta axis. So this coordinate system is not connected with time. Both these axes are not dependent on time. They are just two axes, orthogonal axes in space. So therefore it's called the spatial coordinate system, because they just represent projections of some time signal. And because these are vectors in the space coordinate system, these are called space vectors. These vectors at every instant of time, which are forming a circle here and continuously rotating, they are called space vectors. This signal, which we started with, these two signals, the sine and the cosine, which are evolving along time, they are time signals. And these time signals were then put into two different planes. The sine signal was put on the vertical plane and the cos signal was put on the horizontal plane. So here the time signals are represented in orthogonal planes. So two time signals, then these time signals were represented in orthogonal planes. Here also the axis of evolution was the time axis, and then we projected the instantaneous amplitude onto a spatial coordinate system alpha beta axis, and we saw that the projected equivalent resultant vector had an amplitude of 1, provided these two waves were sine and cosine waves of unit amplitude. And this vector kept rotating continuously with the time evolution. It started along the alpha axis, and in 90 degrees it reached the beta axis when the sine has reached the maximum. And then as time progresses, this vector completes a complete circle. So once the sine wave has progressed and completed one complete cycle, this vector, the space vector, has started from the alpha axis and made a complete circle and come back to the alpha axis again. So what we have achieved, the takeaway is that time signals are now converted into a space vector. The time signals can now be represented as a spatial vector or a space vector rotating in space. Now this is the concept that we would be using to convert AC signals to DC. Consider the alpha beta spatial coordinate system. I have alpha and I have beta. Consider a vector in this spatial coordinate system. This is a space vector. Now let this space vector have an amplitude r, and it is at an angle theta. So in this fashion, and this space vector can be represented in vectorial form as r, like this. Now this r can be written as amplitude r e to the power of j theta in polar form, which is nothing but r cos theta plus j sin theta in this fashion. Now this is the representation of this r using the variables r and theta. Now consider another coordinate system, and I am calling that one as the d axis and the q axis. D and q are orthogonal. This is another coordinate system having the same origin, only it is displaced from the alpha beta coordinate system by an angle rho. Now in this new dq coordinate system, how do we represent the same r in terms of the alpha beta representation? Now the vector r in the alpha beta coordinate system is represented as r e to the power of j theta, same as here. Now this r in the dq coordinate system can be written as r e to the power of j theta minus rho, because this theta minus rho is this angle, and I can write it as r e to the power of j theta into e to the power of minus j rho. Now r e to the power of j theta is nothing but the alpha beta representation. I will write it as alpha beta representation into e to the power of minus j rho. So rho here is the only variable coming into the picture, and that rho is the displacement of the new coordinate system from the old coordinate system, or I should say the displacement of the dq coordinate system from the alpha beta coordinate system. So using only the displacement angle of the two coordinate system, you can write the representation of the vector in the dq coordinate system is equal to representation of the vector in the alpha beta coordinate system into a transformation factor e to the power of minus j rho. This is one thing. Or I can say representation of r in the alpha beta coordinate system is given by representation in the dq coordinate system into a transformation factor e to the power of j rho. So here it is minus j rho, here is j rho. So one is the forward transformation, another is the reverse transformation. So this first one is alpha beta to dq, alpha beta to dq transformation. The second one is dq to alpha beta transformation, reverse transformation. So these are the two transformations that we will be using to go back and forth. What we are going to do is, this vector we saw was a vector which was rotating in a circle, and then we will make dq also to synchronize with r and keep rotating. So the vector is rotating in a circle, it is going at speed omega t, so the angle theta is going at omega t. We will make rho also go at omega t, so it looks as though d is following this vector r synchronously. Then the angle between r and d will be same at every instant of time, though both are rotating. So if someone were to jump onto this dq axis and then they are sitting on here and viewing, always the projection of this r vector onto the d axis is a constant, projection of r vector onto the q axis is a constant. So instant by instant you will see that there is no change as long as r doesn't change, and you will see, for someone sitting on the d axis, everything is seen as dc. Once the person jumps back onto the alpha beta axis, this is rotating, and then for everything will be seen as a sine and a cosine wave. So this is the principle that comes into being, and this is how we convert AC signal into DC and then do the control action here and then jump back. So all the controllers are kept in the DQ axis, reference axis, which is rotating at omega t, or at the rotating at the same speed as the r vector. So this is the DQ axis theory principle. Let us consolidate with few conversion equations, and then we can write down the block diagram.